All right, we're rolling. How's everybody doing? Everybody got my email about the course webpage? If you didn't, then what does that mean? Yeah, you're not enrolled. Okay, so we'll go through the course webpage. So if you've already taken classes from me, you know pretty much how things go. So here's the course webpage. Just to make sure that you can follow, if you go to cmosedu.com and you click on courses and you click on spring 2019, and then here's the lecture notes and videos, which I will record every lecture like I'm doing right now, evidence. And then I will also scan the notes in and post them online so that you can review when you want. And how you doing, man? All right. So that you can pay attention in class. This semester I bought a new computer. It's got a solid state drive and faster, more RAM, and then I upgraded the Camtasia. So the screen's going to be bigger, but it may be a problem when reviewing it on your laptop because it may be too big. So I need the little feedback there if it's too big or not. I don't think that's a problem. There's probably a way to shrink it, but it's definitely easy to make it smaller. So look at that next time. Homework is right here, pretty much. Homework assignments will be every day, as will quizzes, so that you actually learn, get through the class. We have a homework assignment due on Monday, one on Tuesday. Note, I will not come into class and say, hey, guess what? You have a homework assignment due on Monday. I'll assume you're checking the web page and you expect it, okay? All right. So let's, current grades will be posted here. So if you haven't taken a class from me, what will happen is, and also if you haven't taken a class from me, I'm very particular about the homework guidelines. So here is how they're put together, and James put that together. Thank you. When you turn in your homework, you'll turn it in folded so that the grade will be on the inside. So if you don't want people to know your scores in the class, don't show them your grades, because when you go back over here, just ensure there's no mistakes. The grades will be listed as what your score is, and you'll be able to identify yourself by your test scores and by your quiz scores and your homework scores. If you have the same scores as somebody else in the class, what does that mean? You have the same grade and it doesn't matter which one you are, right? Well, am I the top one or the bottom one? Who cares? Now, there may be the rare case where you have different grades, but that's because of rounding in the spreadsheet, okay? If they give like a 9.5 and the other gets a 10 or something, and you're right on the border, but all right. That way, if there's a mistake made, you can see it, and then you don't get penalized at the very end. Everybody cool about that? All right, in this course, we'll use LTSPICE. Just out of curiosity, is anybody not a guru with LTSPICE? Kyle? Anybody? Bull! I know there's people in here that don't know how to, you know how to use LTSPICE. All right, so I'll do some examples of LTSPICE today and other times. So the first few homework should be not, I don't know what's painful anymore. Shouldn't be too painful. Everything I do in class will be zipped up and put here. So when I do examples today, I'm going to zip them up and put them in this folder, and then you can go home and download them. Let's say you don't know how to use LTSPICE. You can click on this link right here. Then you can go to these tutorials and other stuff, and then you can watch these videos. And you can go to the 220D LTSPICE, and there's videos and PDFs, a little bit more extensive, and examples for lots of stuff. Okay, but you should be able to figure out how to use it from what we do in class. But what the hell do I know? All right, I don't think think LTSPICE is nearly as complicated as cadence. Would you say? Yeah, it's a lot easier. All right. Let's see what else. Office hours right here. Note, if I am not going to be in office hours, I will put a note there and I will say, I will not have office hours on this day. Do not email me and do not ask me, hey, are you going to be in your office hours today? That actually offends me. All right. I am very reliable. Semper Fidelis. Right? Always faithful. If I'm not going to be there, it's because there's some major problem, like I got in a wreck or something on the way to school or something. Let's hope that doesn't happen, all right? But I will be there, all right? So you don't have to worry about if I'm there, oh, I need to talk to him. Is he going to be there? All right, I will put it there if I'm not, all right? Where were we? We'll see who gets the lucky job of being my TA for this class. That'd be fine with me, but I don't think, I don't know if that'll happen, but that would be good. I'd be happy with that. No, he can't be a TA. One other thing. I almost travel every week, and so I will try not to miss any lectures. Right now, I don't have any plans to miss a lecture. I said Semper Fidelis. Did anybody know what that means other than one person? Yeah. It means Latin for what? Always faithful. So Semper Fidelis, right? You looked at it.
It means that you're a Marine.
Well, yeah, that's the Marine Corps motto, but it's also Latin. So, all right, it's like saying rock on. Well, it's two words, rock on, but it doesn't mean that, you know, maybe somebody's saying in a group, but it doesn't mean it's not also plain English language. So, all right. And I take pride in that. So, all right, grading, midterm, homework, quizzes, course project. For 620, you're going to have a more complicated project. And then the final. Let's see, all this stuff. I don't think you guys are pretty mature students, so I don't think there's going to be any issues with people playing with their phones, right? If I give a quiz or a test and I say open book, you can't use your computer in a soft copy. You can't share a book with somebody else. You need to actually have the book, all right? So don't think that you can print it out or scan or take a photocopy of it. Wait, you have a laptop open there? Please close that. I was just saying, I was thinking I don't even need to cover this. I guess I do. No laptops or internet appliances used during lecture. All right, man, my daughter is a professor at University of Colorado Boulder. She's a civil engineering professor, and she says, Dad, you're mean. And I'm like, no, I'm not. She lets her students do all that. I'm like, yeah, you do what you want. Yeah.
Your son's still the principal of the students?
Yeah, he was in Charleston. He won a position in the Florida Orchestra. So last year he moved to St. Petersburg, Florida. Yeah. Yeah, making a job as a musician. It's good. Hard. All right. Let's see. Don't cheat. If you have questions, email the Google group. If you have questions for me, please talk to me. I'm sick of electronics. Isn't that funny? I don't have any social media. You want to see my social media? Yeah. There it is right here. My picture once a week or so. Something we did, all right? You notice anybody in here? That's my wife. That's me. That's James. Other people. Let's see. Who's this guy right here? And this guy right here. This guy right here. This guy down here not even paying attention that there's a picture going on. All right. From the other side, though, you can see the other people. All right. So let's go back here. All right. Any questions before we get going? Today's homework is on Chapter 9. Here's read Chapter 9, Models for Analog Design Square Law Equations. Does anybody have any questions before we get going? Anybody wondering about the grading? Like, I'm in 620. What's going to be the difference between that and 420? Who's in 620? I don't think it'll be that big of a difference, but we'll see. All right, so what I want to do now, I want to go through some basic circuit stuff, and I want to review transistor operation because I have this phobia. I lay awake at night and think people don't understand transistors, and I'm pretty much correct. Well, you tell me. And then I'm going to do some SPICE examples and other things. But if you look at the first part of chapter 9, it's about IV plots. So in industry, IV plots are used to characterize data, or used to characterize a device or a circuit, okay? So we're going to do a few examples there. First thing I'm going to do is I'm going to plot. I'm going to ask, when I do IV plots, well, let's actually do a simple example. If I plot a diode on an IV plot, and here's my diode, and I've got plus minus VD, and then I've got I here, I'm gonna call ID, and I want you to plot the diode plot, or plot the IV plot for the diode. First thing, tell me what to write on the axes. How do I label? Is it I and V or what? Don't all scream it at once. VD and ID, yep. So now if I do the IV plot for the diode, most of you just took 320, right? So what do I get? Goes up like this, where this is like 0.6 volts. And it goes this way, and there's a little bit of a leakage. We call that the scale or saturation current, correct? Anybody challenged by this or not seen this before that will admit it? So I want to be able to look at these different things and tell what does the diode look like in certain regions. So if I say the diode here looks like a voltage source in parallel with the resistor, the diode here looks like an open or a current source, I want you to understand that, all right? So let's go on the next page here, and let's go write I and V, and I want you to plot the IV curves for a voltage source. What would the IV plot of a voltage source look like? Here, let's write a voltage source here just so you know what I'm talking about. What does the IV plot of a voltage source look like? Yeah, it'd just be like this if it's positive, right? What about a current source? I know this is kind of fundamental, I hope. What about a short, a wire? How much voltage can you generate across the wire? Zero. So the current can change though, right? That's circuits. So I get this. Everybody agree with that? So an ideal diode, if you recall when you were learning electronics, it turns on at 0 volts and goes up and infinite and current can flow. What about a open? How much current flows in an open? All right. So this is an open. What about a resistor? All right, should be a linear line. Oh wait, everybody knows there's 14 people in lab, and we're having lab today because you got my email. All right, you think there'll be a quiz? What's the slope? There'll also be a lab. What's the slope? Is it R? 1 over R, right? So the slope is 1 over R. And that's the resistance. And so when I have an IV plot and I look at it, I say it behaves like a resistor here. What am I thinking? It's got a linear plate. It's got a linear variation. What if I say it looks like a voltage source here? It's going up and down. What if I say it looks like an open, no current flowing through it? Constant current source, flat line. Now I'm going to go through this again later today when we talk about transistors. I'm going to say, hey, the transistor looks like a resistor here. Hey, the transistor looks like a current source here. I want you to understand that based upon this plot. Any questions? Okay, so I'm going to do some examples here first, which I think are in your homework. And what I am doing is I'm going to have, let's do a simple one to begin with. Let's say that if you go, and let's sketch it like this. And this label, why do I label the x-axis voltage and the y-axis current? No, why? It's not standards. There's a reason. Why do I have voltage on the x-axis and current on the y-axis? Yeah, because current's a controlling, or voltage is controlling the current in a device like a MOSFET. I apply a voltage and I change the current through the device. So voltage is a controlling thing, that's on the x-axis, and what's controlled is the current on the y-axis. All right, so here's what I want to plot, and I'm going to plot it like this. This is the current going in. This is plus minus V. And so I put here I. And now this is a little challenging for people, so I'm going to go through this slow for the first few of them. So if I look at this, and now one more time, everybody knows I'm going to scan the notes in. I'm going to post them online, and there's the video. And everybody knows you can watch my videos at 2 times speed, and it sounds really funny. All right. So what point should I plot first? I can plot any point I want here on the y-axis. I pick a voltage, right? Why don't I pick 0? Everybody agree with that? It's a good point. How do I put 0 volts here for V? I put a wire across it. So this is V equals 0. Everybody okay with that? So if V equals 0, what's the current I? Is it minus 1 milliamp, right? So I'm right here, minus 1 milliamp. Now there'll be a quiz on Monday. What do you think it's going to be on? This, I think. I made it like a week ago. I was paranoid. I wouldn't have time to do stuff. All right, so that's my first point. What should I do next? Well, wait a sec. What do you think the shape of the curve is going to look like and why? It's going to be linear. It's not going to be curved because this is a linear circuit. There's no transistors or diodes. Everybody cool with that? Okay, so it's a linear circuit. It's going to be linear. So why don't I pick something easy? 1 volt. Why don't I go up here to 1 volt and then I redraw the circuit just because I'm learning. I have I. I have 1 milliamp. Now I put 1 volt here. What? 1 volt. And now I ask, all right, how much current flows? Okay, so I have 1 volt here. Then I have plus, minus. Well, wait. Is there ever a situation where I'm going to be able to have 0 current? Look at that and ask. There's never a situation where I'm going to have 0 current, right? Why? When I connect something here in a voltage, I'm always going to have a current flow. So if I ask now, what is the current flow when I have 1 volt there? What is it? 2 points determine a line. I'm done. And I can go figure it out. Go over here to -1 and say, hey, no matter what voltage I put here, I'm going to have I equals -1 milliamp. That's easy, right? There's my IV plot. Now, let me ask this. Is there a place on the voltage x-axis where I can apply an open for my V voltage on the x-axis? No, an open's not a voltage. I can change the voltage across an open, right? So there's never the situation where I won't have something there when I'm doing an IV plot where I have 1 milliamp flowing. Everybody follow that. Let's make this a little bit more interesting, if that's possible. Let's pick, how about this circuit right here? What do you think? Exciting? So I'm going to sketch my IV curve. And I'm going to go over here. And I'm going to ask, okay, tell me what to do to plot the IV curve for that circuit. Let's try V equals 0. That's easy, right? So here V equals 0, I'm going to be right there. I'm going to short across it. How much current flows in the 1K and Y? Y, 0. Yeah, it's a short across it. Both sides are at the same potential when I short across the device. Okay, so then what's this potential right here? If I make this my reference. What's this potential? It's 0. Why? Shorted. So now here's where I cringe. What's this voltage? You really want to make me cringe. Okay, well, see, I was waiting for somebody from my 220 class to say, I don't know. And I'd be like, not enough homework. So that's -2, right? So if I ask what, now let me pause because this is where I want to make sure nobody gets messed up. So what's this voltage again here? 0. So I'm going to do this like 3 ways or a couple of ways anyway. So I want to know what the current flow is. So I'm going to put the current flowing here, I, in this direction, and flowing I, and then what's the I down here? What's this current? 0. I'm repeating myself. I apologize. Okay, so now I ask, oh, well, what's the current? The current I is this voltage plus minus -2 minus 0 over 1K, or -2 milliamps. Now let's go ahead and label it. Looking good? Let's do that again. Let's say I define the I like this, and then I put the plus and minus here. So I don't know what the I is, I'm not paying attention to that. And I ask, all right, well, what's that current? That current would be this voltage, 0, minus this voltage, -2 volts, over 1K, or 2 milliamps. Everybody follow that? Well, it better be the opposite because I drew the arrow the opposite way. Then I follow that up. I go over here and I say, oh, well, that's -2. Okay, what I did was correct. Any questions? Does that make sense? Let's go over here now, and let's say that I'm going to apply a voltage. And instead of applying 2 volts or something, let's just apply 1 volt. Now notice I changed colors. And maybe I should draw a separate circuit, but I'm lazy, so I'm not going to. What's this voltage here? And then what's this voltage here? And then what is this current going down here? -1 minus 0 all over 1K, or -1 milliamp. And is that in the same direction as our input? Yes, so what do I put here? I put -1 milliamp. And I go, oh, linear circuit, 2 points, boom, done. And I'm going to pause and simulate this. All right, any questions on this? Because I'm going to make a more elaborate one. And I make it look easy, but when you get the quiz, you do the homework. Let's see what the homework looks like, actually. I haven't looked at that in a while. Boom, boom, boom. Everybody knows I'm not going to tell you, I don't know if I said this already, I'm not going to tell you that there's homework due. So these are a little bit more elaborate circuits. All right, but maybe we'll work one of them just to prove I can do it. All right, so let's take a picture with your mind's eye of that circuit, 2 volts, 1K, 1K. Let's go over here to LTSPICE. I'm gonna go a little slow, assume everybody is, there's new people. How's the lab time? Do you like it this time, or do you like it when it overlaps classes during the day? It wasn't overlapping any classes? Oh, it is? What? What's it overlapping? Screw that class. Your system. All right. What is 450 anyway? Oh, okay. All right, who's taking that? All right, I'm going to be quizzing you this semester after you get through, and you're going to tell me what you went over, and I'm going to say sketch the energy band diagram of a p-n junction, and then when you mess it up, I'm going to make you feel bad. No, I'm not. When does that class go? What time is the 450? You know the problem is, how are you going to get my lectures at the beginning of the class? Is somebody going to be able to videotape that? I don't know. I think you should not. I think you should drop 450. Lecture 1, example 1. What's that?
Are you free to do the lab at 8 in the morning on Mondays?
Well, there's probably something else that time. You know what I'll do? Man, you're going to think I'm super nice. I'll record the lectures at the beginning. They'll take the quiz when they come in. Holy crap, I work hard here. All right. So, all right, we got a voltage source. And then this was 2 volts. The problem is, now that I do this once, everybody will be expecting it. And then when I don't do it, they'll be like, wait, well, you did it last semester. How come, don't you like us? Or what's I'm like, oh. All right. At one point, they were supposed to have these you could record your own videos in the classroom, and that never came through that I know of. All right, let's add a ground. I just zoned out there. I think you have to do another video. Anybody that's never used LTSPICE, did you follow what I just did? Who's never used LTSPICE? I know there's somebody in here that hasn't. Will anybody admit it? Come on, man. All right, well, maybe I'm wrong. All right, so there's my circuit. Everybody agrees? How do I do the IV plot then? DC sweep, but I don't have a source to sweep, do I? I'm going to add one. Yay, I like that. And then let's put a wire in. Okay, now on a pause and make sure you understand what I'm about to do, because if you don't, your homework will be challenging. You see in the homework, it's going to be how the current's going in this direction. And the voltage is plus to minus. What does SPICE define positive current flow as? Plus to minus of the voltage source, right? So I need to either put a minus sign when I do my plot or add another dummy voltage source in here that I can just plot the current through. What would you prefer? Let's do it both ways. That makes me work more, right? All right. Students like it when I work. So I'm going to do a dot D, or actually instead of writing it manually, I'll poke the running man. And then that's what the author of LTSPICE calls it when he runs the sim. So I'm going to sweep V2 from, let's do a linear. And then I'm going to do a start value of minus, let's live it up and say 4. Stop value of 4, increment of 1 millivolt. Hit OK. And then plot the current through there, which is the opposite of what I want. I'm going to right click on that. Go over here and hit minus, and then I'm going to go check my plot. I see at 0 volts. What is my current? Minus 2. So I'm going to go to 0 volts, and do I see minus 2? Yes. So you know what I'm going to do? I'm going to do this. What's that? All right. Yeah, I'm going to go, hey, I want to get a good grade. Snipping tool, let me right click on that and say pin to the taskbar. So I don't have to keep doing that. I'm going to do a snip, new, go over here. And I'm going to go, so I'm going to put my current in here. And I'm going to go up here and put an arrow. And I'm going to put 0. You get the idea, right? Etc. But you're going to be nicer than, neater than me. Of course, what's the other way to get an image in LTSPICE? Window or tools, copy bitmap to clipboard. All right, so we'll hit save. Then we'll hit save. Any questions on that? Oh, I told you I'd do it a different way. Oh, I just went over something and didn't tell you subconsciously. So you see this file PLT here? So when I run the sim, it automatically plots, but to ensure that I select the waveform and then I hit save, and that generates a file and that pops up automatically. Also, notice the lines are a little thicker. If I go over here to tools and I do control panel and I go to drafting options, I can set my line thickness to say 10. If you really like crayon size lines, or what I preferred, what I set it to is 3. And I also can go over to here and do my color preferences, which I've already changed when I was checking out the computer this weekend or Monday, and change the color so that I don't have a black background, which eats lots of ink. All right. The other thing I said I would do is, let's get rid of that. Let's go over here. Let's go File, Save As, and let's put this example 2. Said I'd put in a voltage source that I can measure the current with. If you know all this already, I'm boring you, I apologize. I'm going to do a Control R. Positive current flow is from plus to minus. So I want my plus here and my minus here. Plus here, minus here. So I'm going to do a Control R until it gets where I want it. Plop that down in there. Call it measure. I want to leave it at 0 volts. Why? I don't want to mess with the circuit. It's a 0 volt voltage source is a wire. Then I hit run. Then I go boom, and then now it's in the right direction. And hey, it works. All right, boring. Okay. Let's do one more from the homework. Yes?
I think your hand calculation was a little bit off.
It was? Crap. What did I do wrong?
It should intersect 0 current.
Oh, all right.
You just forgot to stick the resistor.
Oh, you're right. Thank you. Yeah, see, even I got a 0 on the quiz. So correction. So this was the 1 milliamp, and then I have 1 volt across here. And then that pulls 1 milliamp that way. And then this current is 1 milliamp that way, which is the opposite. So it'd be 1 milliamp this way. And then what's the total current going in this direction? I equals 0. Oh, I got to redeem myself now. See how easy I messed up? All right, let's do one of the homework. See if I can do it without messing up. I got to get a good quiz grade now. Thank you. All right. So let's go over here. And which one do you want me to use? All right, we'll do the last one. Just don't let me make any mistakes. I know I'm not switched over, but if I switch over, I can't see the last one. So give me a second to draw the schematic. This one looks hard, though. I was hoping I wouldn't have to do this one. All right, take a picture of that with your mind's eye. 1K, 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 2 volts. All right, everybody agree with that? Looking good? Okay, and so let's start with, let's not do the IV plot until the end. Let's start with the easy one, which is a short. And if that's the case, what's this voltage? 0. And what's this voltage? But I don't know anything else. So let's see, I want to analyze this circuit. So now I'm going to see how good your circuit skills are. Tell me what to do. I need to do my simple circuits 1 procedure. No. Yep, I pick a direction of current flow. Let's pick, since our current's this way, this is where you get it on there and you just stare and you go, oh my God, I can't do it. All right, so I pick a current flow and I'm going to pick this way. Why did I pick this way? It's the same direction as my input I, right? All right. So if that's the case, what do I do next? Plus minuses, plus minus, plus minus. And what's the voltage drop across here? And what's the voltage drop using Ohm's law? And what's the voltage drop across here? And now I'm going to get on my running shoes here. And I'm going to start running. Here I go. Why don't I run through this branch again? Short. So I go up here. Yeah, the problem is if I do the video, then you're going to have to watch that before you start the lab. So you're going to be sitting in the lab watching the video, so bring your headphones. All right? I hate hearing my voice, especially at times 2. All right, so I go over here, and what do I write first? Am I going up or down, plus to minus? So I write... Okay? Wait, what? Here I am. Minus 2. And then here? Anybody agree with that? That problem's unreasonable, man. So far, so good? What next? Yep, let's pick another voltage source. You know what? Since I see 2 volts there, I'm going to use my circuit skills, and I'm going to put, and let's use something more noticeable. I'm going to put 2 volts. Explain to me why I did that. What's this voltage? What's this voltage? What's this voltage always? What's the current through the resistor? 0. Oh, life is good. See how when you know what you're doing, how easy it is? All right, and so now I've got the same thing, except I'm going to pick my currents. And here I get current going this way, and it's I times 1K, different I. And this one is I times 1K. And I'm going to get my running shoes on, and I'm going to run, and tell me what to write. 2 volts. Then I don't think these are that hard. Then what? And then what? I already like this problem. So at 2 volts, I equals 0. Yay or nay? Did that problem, is it as bad as it looked? What? Yes. Did I do it wrong again? Oh, you're right. Thank you. Ah, man, I'm going to fail this class. Yeah, I was checking to see if anybody was paying attention. Holy crap, 2 examples, 2 mistakes. He sucks. All right. I'm not going to sim this. Is that okay? All right. Let's move on to MOSFETs. Any questions on these? So you have IV plots. So I'm going to go over qualitative MOSFETs. Oh, before I do it, shoot. Are there any questions, or does anybody not feel like they're a guru with MOSFETs? You don't feel like you're a guru? You took 421 from me. I'm just joking. All right. So I'm going to go give you an explanation to make sure you understand them, all right? I like honesty. I want you to be walking around the hallways like this, like you're a guru, all right? Wearing your transistor-adorned robes. Different is good. You know, I don't know if I've told you this story before, but I fly almost every week. And one time I was getting on a plane back from San Jose, and because I fly a lot, I'm usually one of the first people on the plane. And the guy came in like 2 or 3 people after me. The plane's empty, and I sit down in row 2, first seat on the aisle, so I can escape quickly. And he comes in and he sits right next to me. So it's a tire empty plane, and he comes and sits right next to me, and I'm like, it's probably not going to be full. And he goes, well, I want to get out fast or whatever, and I'm like, he goes, is that all right? And I'm like, no, different's good, man. We had a good conversation. It made the flight go by real fast. But if you don't know this, different people have different personality types. So if you go to a movie theater and you're the only person in the movie theater and somebody comes and sits next to you or whatever, they often do that because they feel better when they're with people. See, I didn't know that till I took a little class on learning styles and all that. So I was like, what the hell? Why is it next to me? And they actually feel better when they're next to you. Just like when you're in the gym and you get on the treadmill, somebody comes right next to you and they're like, oh, and I'm like, hell, dude. Especially if it's a sweater. You know what a sweater is, right? All right. What? Yeah. I like space, man. All right. Different strokes for different folks. All right, so I want to give you my example here. So here's my house, and then here's my hose bib. Did anybody take 320 with me? You did? Okay. All right, so I want you to imagine you're standing in your yard or somebody's yard and you're turning on a faucet, okay? And no one's looking at their phone, right? Yeah. All right. So I want, what's that? I don't care. That's still looking at your phone. There's your water. Here, let's put water. And there's your voltage. And I'm going to put turns of the hose bib. Okay? So I'm standing in my house, and I want you to remember this because we're going to use this in the lab. We're going to use it over and over in this class. I'm standing in the house, and I start to turn the hose bib. All right? So what happens? Nothing immediately, right? Unless you got a broken hose bib. So you start turning, and then water starts to come out. And the more you turn, what happens? More water comes out. So if I plot that, and I get something that looks like this. All right? I'm going to do the same thing with a MOSFET. So MOSFET, this is the drain, this is the gate, and this is the source. Now there's a water supply connected to your house, right? So I need a water supply connected to my MOSFET. And I'm going to call that VDS. Voltage between the drain. What would I call this voltage then? V drain, this voltage V source, and then this voltage plus minus VDS. Everybody follow that? Okay? Then I got to turn it on. So what I'm going to do to turn the MOSFET on is I've got to go VGS and I've got to apply a voltage. So here with my MOSFET, I'm going to apply a VGS, and when I get to the threshold voltage, V threshold N, the MOSFET is going to turn on, and I'm going to get a current to flow. Everybody follow that? Okay, so the equation that I'm going to use for this is ID equals Kp sub n over 2 times W over L, which is the size of the MOSFET, which if you won't know what that means, but unless you've taken a layout class, but it's just how you size the dimensions of the MOSFET. VGS minus V threshold N. That's the equation that describes that. So notice when VGS, this equation is only valid for VGS greater than what? The threshold voltage. Because what's the current that flows below the threshold voltage? 0. That's easy, right? So there's another thing. This is assuming that VDS is greater than or equal to VGS minus V threshold N, which means saturation. So I got to make sure the MOSFET turns on, and I got to make sure there's enough water pressure. Because wait, let me think. That water company's got a crappy line to my house. The water pressure going to my house isn't going to be good. When I go to do this curve, I'm not going to get the curve because the water pressure is going to drop and maybe flatten out, right? So I got to assume there's enough water pressure here to keep the MOSFET operating in saturation. All right, we all follow that? So I'm going to go over these more later, but this equation and this equation are required for this one. Now I want to do a homework problem, or I want to do something similar from the homework problem just to use this equation. When I plot this, because there's going to be another one I'm going to go through, it's ID versus VGS, and this is the plot, and the way to remember it is this is the one where I'm standing in the yard and I'm turning the hose on and I'm plotting the current that goes out. I'm at the gate of the MOSFET, I'm applying a voltage, I'm increasing the voltage until current starts to flow in the MOSFET. Does everybody see that? Okay, so let me just take a quick look at the homework that we have. Make sure I'm not crazy. All right, let's just do, how about let's do this one? Or actually, let's do this one. This one, what is the drain current and why? So that's called a diode connected MOSFET. The gate is shorted to the drain. So this voltage is going to turn on to whatever it needs to source or sink the 20 microamps. How much current flows into the gate of the MOSFET? 0. So if no current flows into the gate, what's the drain current? 20 microamps. How do I calculate? Well, let's do this. I'm not seeing enough response. I'm having a nightmare here. Told you, what do I lay awake at night? Thinking people don't understand transistors. All right, so let's use this one. Okay, I'll switch over in just a sec. What's transistor stand for? Transfer resistance. Has anybody done this homework problem already? Come on. So it's a 10 micron, and I'll switch over in 2 micron. And if you look, says these are Book's long channel MOSFET models. So there I've got my, shoot. That's 20 microamps and 5 volts. All right. Quality sketching there. All right, so I'm going to write my equation. ID equals Kp sub n. What's Kp stand for? Transconductance parameter of the n type. So there's a Kp sub p over 2 times W over L times VGS minus V threshold n squared. Just out of curiosity, has anybody not seen that equation before? All right. So I want to find VGS. What's ID? $20 micro. I'm getting scared here. Let's assume VGS is 0. Pay attention now. VGS is 0. What's the state of the MOSFET? Off. No water's coming out that hose bib. There's no water coming out or going through the transistor, no current flowing through the transistor. Where's this 20 microamps flow? And there's nowhere for it to flow. It flows down here and then pulls this node up until that current, the current that the MOSFET can sink, is equal to 20 microamps. And again, this is called a diode connected device because it's going to just pass whatever current, when you put the current in the right direction, it's going to pass whatever current is connected right through it. Any questions there? Okay, so now I need to find, the only thing I don't know in this circuit is VGS. Tell me how to find VGS. Solve for VGS. I get VGS equals, let me see, square root of 2ID over Kp sub n times W over L plus V threshold n. So VGS will always be at least V threshold n. Okay, then I'm going to go to the book. It said long channel process. I'm going to go to the back of the book. Let's see, back of the book. And it says for the long channel process, let's see, I need to know Kp. The Kp sub n is 120 microamps per volt squared. Oh, that actually looks clearer on the screen than it does with my vision. I don't know how that's possible. And the threshold voltage is 800 millivolts. Everybody see that? 120 microamps Kp, threshold voltage. All right, so I'm going to go back over here. And I'm going to write, oh, well, that's 2 times 20 microamps all over 120 microamps per volt squared times 10 over 2 square root plus 0.8. Where did I get the 120? Back of the book. So I go, oh, let me see if I can do this without a calculator. Calculator's evil. I get 40 over times 2 over 10 times 120 plus 0.8. So this would be, cancel that 0, and I get, cancel the 4, and that would be 30. So I get 2/30 plus maybe I can't do it without a calculator. 2/30 plus 0.8. So let me think. 1/10, 2/30, 2/3 points. I think that's 0.066 volts plus 0.8. Does anybody want to verify? What is it? Oh, I had to do the square root. Shoot. Let's just use a calculator. What is it? Thank you. 1.06. Wait, what is it? That doesn't seem right to me. Not that I don't trust you. Let's see.
1.058. 1.058.
What? Oh, no. Oh, all right. I was just, what's this? I'm going too slow. 0.258, and then plus 0.8 would be 1.058. I thought you were just saying this was 1 point something. Okay. All right. I'm like, I don't think that's right. All right. So let's verify that in simulations. Okay, so let's go, because I'm lazy, go File, Save As, Lecture 3. I'm going to do this from scratch. I'm going to hit the minus, and actually I'm going to do it from scratch. So let's get a voltage source here, voltage, okay. And then let's get a current source, current, okay. This one's 5 volts. And this one is 20 micro. And I'm going to grab a 4-terminal MOSFET. Does it bother anybody? I didn't put it in the same direction. Let's do it just so nobody complains. He didn't do it the way that it was drawn in the... Who knows, man? People love to complain. All right. Not any of you, right? Not yet.
Engineers.
Okay. Let's go ahead and label this VGS. And then here's where it gets challenging. When you did 320, did you do LTSPICE for transistors? Okay, so this is a little bit challenging. If you right click here, you can put the length and the width, 2U and 10U. Okay, we need to change the model name. If you go look at the, If you go look here, here's the SPICE models. The long channel NMOS name is N1U. The long channel PMOS name is P1U. And here's the short channel MOSFET names for in the book. You see the model file in the folder. When you do your simulation, unless you have a path, you need to put the path to the models or else things won't work, or it'll use the wrong models and mess things up, and you'll be like, it's simulating and it doesn't look right. So putting the models in the correct place is important. Okay, and I'll do that in a moment. Since this file is in the same one as this, All I need to do is put dot include CMOS EDU models. Hopefully that made sense. So I'm going to call this what? If you don't do this stuff, you're going to waste a lot of time. Okay, and now I don't see those sizes, right? So this one you got to remember, and it's on some of the help, but I'm going to press Control, right click, Control, right click, and then I'm going to double click right there so the sizes show up. All right, everybody see that? Then I'm going to do a different simulation this time. I'm going to do an operating point. And it says, oh, because I didn't include the models, dot include CMOS EDU underscore models. I told you to do it, and then I didn't do it. Do as I say, not as I do.
Well, you were just showing us what happens.
Oh, yeah, there you go. All right, so we hit run.
Good teacher, man. You show us the whole place.
Yeah, and then you hit VGS, and you see on VGS I calculate with the more complicated model 1.07, so I'm off by 20 millivolts. Is that acceptable? Of course, it's really acceptable for the small devices. Any questions on that sim? All right, and of course, where will you have these? On the course web page. Okay, we ready for another one? All right, so let's do the following. Does this make sense? With the standing in the yard, here you are standing in the yard, you're turning your hose bib on. Let's just pause because I love doing this. Images. Did anybody know that's what that faucet's called? If you look on some of the concrete foundations, when they pour the concrete, after they pour the concrete where they put it, they'll write hose bib, tell you where to put the hose bibs or other things. So, all right. What'd you learn today? I learned what a hose bib was. You don't know what a hose bib is? What's wrong with you? Go to Home Depot. Where are your hose bibs? What? All right, so here's the other one. Let's say that you graduate, you live in Vegas, so you're lucky. So you decide you get a job, you're gonna buy a new house. All right, so you have a new house and you get it built. What's that? Don't get depressing on me, man. You're never gonna graduate. All right, so your new house doesn't have the water connected, right? And so in the house, it goes over into the street, and there's, towards the street, there's a little place that's your main water valve, right? This is your main that you can shut your water off in the street. And if you buy a house or live in a house, you should know how to shut your water off, man. That's really important. Okay, and you should have the tools ready that if it's an emergency, you can run out to the street and shut the water off. Okay? All right. Don't be one of those people, help me. All right, so here you are, and you think to yourself, hey, my new house has got brand new plumbing, and that brand new plumbing all has never had water go through it, so I don't want to drink, and I don't want the crap to be in my pipe. So what I'm going to do is I'm going to come in my yard and everywhere else, and I'm going to turn the water on, the valve's on full blow. So then I can flush the system, right? So I turn them all on, and then I go out to the street. Here I am walking out to the street. And I say, all right, I'm ready to flush my house. So I go out there and I get my little tool, or I reach down in there because it's new construction. There are no black widows. And I reach down in there and I turn on the water. So now my hose, I'm looking at this as my transistor, my hose bib, right? And so I'm going to plot the water that comes out of my hose bib, I, versus the turns. Versus the water pressure applied to the house. But I've got to turn this on at some level, right? So I got to turn it on a couple turns. So I turn this on. So let's say 2 turns. And then I increase the water pressure. which is, we're gonna find out VDS. So I go out here and I start to increase the water pressure. Well, we don't get any water pressure to the house until water starts flowing in, right? So water starts flowing in, and then what immediately comes out? As soon as we start getting water pressure, what immediately comes out? Yeah, water, dirty water, whatever. So it starts coming out. What does the transistor look like in this region? A resistor. And what's the resistance? 1 over that slope. Everybody agree with that? Now, we keep increasing the water pressure, going up, going up, going up. And then we reach a point where we haven't turned this on enough, and we've got really good plumbing and really good water pressure to our house. And then what ends up happening, just to make sure everybody knows, where does the water pressure come from over here? No. How do you get water pressure in the water to your house? What do? Do they? What? No, the water pressure over here, you got a pressure of water going to your house. Where does that come from? The water, okay. Yeah, gravity. It comes from a water tank that's at a higher elevation than your house. Okay? So you look at the water tank out on Desert Inn out west, that's going to be feeding the houses that are down further towards the strip that are at lower elevations. So how do you get the water in? You'll pump it electrically into the tank, and then the water pressure from the tank at a higher elevation is the one that feeds the house, and that's how they regulate the water pressure. There's a huge amount of water there, and so it's easy to regulate the water pressure. It's really simple, okay? So you go to the Midwest, and you drive around, there's no hills. So how do you get elevation? They put the water tanks up in what some are called onions. Water tanks that are up high like that. And so they're pumped up and then they're at a higher elevation. So let me Google that real quick. Let's see, water. Let's just do water onion. No. Water tank onion shape. Anyway, yeah, we can spend more time looking at that. Where has one? Oh, yeah. Yeah. In Meridian, let me see, there's a town up in Idaho, I know that has one. Meridian onion water tank. There it is. Oh, there's another one. Let's look at this one. So this is what it looks like, water tank. All right, I don't want you going through and water comes by magic. There it is. There's the water storage. It goes up high. All right. So back on the farm, I keep increasing the water pressure, and I want my water pressure to be limited by the hose bib. What ends up happening? What's that? Flattens out. And when it flattens out, what does it behave like? Current source. So when we make transistors, current sources, it's going to be operating in the saturation region. And this will be the triode, or you might know it as the ohmic, because it's resistive, or the linear region. And that's where it behaves like a resistor. Now, I need to label this because this was for 2 turns. Everybody agree with that? Now, what if I only had 1 turn? It'd be like this. What if I had 3 turns? So in a transistor, what I have is the following. So these would be VGS 3, VGS 2, VGS 1, all greater than the threshold voltage. And what's the relationship here? What can I say about VGS 3 relative to VGS 2 relative to VGS 1? VGS 1 is less than VGS 2. VGS 2 is less than VGS 3. Turning on the valve less here, turning it on more here, turning it on even more here. See why they have the curves like this now? It's not magic, right? There's a reason for doing that. See why we say it looks like a resistor here and it looks like a current source here? What do you think when we look at it like this, where it has a slope, it'll look like a current source in parallel with a resistor? Any questions on this? Oh, what am I varying here? The water pressure to the hose bib, the pressure across the transistor, the pressure across the transistor. Well, we'll see how the next few days go. My voice is going, and I have to give testimony in a deposition in DC on Saturday, so which is 7 hours. So if I don't have class on Monday, you'll know why, but I probably will have to be almost totally not able to speak because I'll get the microphone and I'll whisper like this. All right, any questions on that? I want to do one more example in the last 3 minutes. Yes? All right, we can ask in lab, right? What? Oh, well, what's the question?
For the mod.
No, that's what I was going to do, PMOS. That's what I was doing next. You read my mind, man. All right, for the PMOS. This is the PMOS transistor. It's complementary from the NMOS. Here's the way I draw it. Let's look at some other ways of drawing it. That's one. Here's another. Yes, it is confusing. The arrow's going opposite of the arrow here. And generally, we apply the supply up here of VDD. Now, to turn the device on, or wait, just to make sure it's clear. So this would be the source, the drain. Notice how it's backwards from the NMOS. So this is V source to drain. Notice it's positive. None of that confusing stuff with negative voltages. Any questions? What do I call this terminal? The gate. And the voltage I care about here is VSG. What's this voltage in what I've drawn? VDD. So if I ground this terminal here, what is VSG? VDD minus ground, or 5 volts. It's the source voltage minus the gate voltage. You see how it's all complementary? The equivalent equation, then you know where to find the variables in the back of the book. ID equals KP sub P over 2 times W over L times VSG minus V threshold P squared. So, real quick, any questions on that? If I have the following, I'm going to sketch it real quick. And I'm assuming I'm operating in saturation, and I say, what is this I? Let's make this 5, sorry. First off, what's VSG? It's equal to 5 minus 2, or 3 volts. What is the current? It's Kp sub P over 2 times W over L times 3 minus 0.9, which is the threshold voltage. V threshold P equals 0.9 squared. What is this voltage here? Boom, done. Any questions? All right, have a good weekend. We'll see you on Monday. Oh, question?
Why does the PMOS model have a negative voltage threshold?
Oh, because when they developed the model, they wanted things to be complementary from the threshold voltage point of view. But if you look at the book, everything is positive, and then but you switch the source and the drain. So for you say VDS, that's an NMOS. You say VSD, that's a PMOS. You say VGS, that's an NMOS. You say VSG, that's a PMOS. Yeah. All right, we'll see you later.